Okay, the next talk will be given by Vincent Froese about two influence maximization games on graphs made temporal. Vincent, please go ahead.
Yeah, thank you. So this is recent work together with Niklas Böhmer, Julia Henke, Yvonne Lazars, Rolf Niedermeyer, and Malte Renken. And what we did is we took two classic games, influence maximization games on static graphs, and just played them on temporal graphs. So what is this? So an influence maximization game is the game theoretic way to model in general the spread of information or influence. For example, it could be opinion diffusion. Think about political parties trying to gain as many voters as possible, or maybe competing companies trying to reach as many customers as possible. Maybe also in the biological context, you can think of disease spreading via this model. So what is the model? In the classic sense, we get an undirected static graph, and we have two or more players playing on this graph. And initially, both players, all the players, choose a subset of vertices in order to influence as many vertices in the graph as possible. So influence in the following means to color as many vertices as possible. And so the payoff of a player is then just the number of vertices she colored in the end. Okay, now the game rules need to specify how this coloring process is actually working, and we considered two examples. So in the following, we always have two players selecting one single vertex, and they do this in the same time, in the step 0 kind of. So in the first game, which is called the diffusion game, here the vertices are then colored by a so-called propagation process. So this means this goes in discrete time steps, so to say. So an uncolored vertex, if it only has neighbors of one color in its neighborhood, then it takes over this color of this player. Whereas if a vertex has both colors in its neighborhood, then it's colored gray. We call this a standoff. So think about this like both players try to influence this vertex at the same time. The vertex gets confused and takes on neither of these two opinions. So he's out of the game then. So this is what we call a standoff. So here's an example, a small grid graph. And if the two players, let's say blue and orange, initially choose these two vertices, then in the first round, what is the coloring? This is the coloring. So these two vertices become blue, these two become orange because they only have this one neighbor. And these two vertices, they have, kind of both colors in their neighborhood. So they become a standoff and are colored gray. So then in the next step, the coloring goes on like this. Here, there's no new standoff. And then finally, this is a standoff again, and this is the final outcome. So this propagation continues until the coloring is stable and nothing changes anymore between two consecutive steps. Then the propagation is over and we have the final outcome. Also, if both players choose the same initial vertex, then they both get a payoff of 0. So this is never optimal to do this. So this is the diffusion game. And we also considered a second game, which is called the Voronoi game, which is quite similar, but slightly different. So here, a player just colors all vertices that are closest to her, closest in the shortest path sense. So same example graph. For the Voronoi game, we take the same player positions. Now there's no propagation process, so this is the final outcome. You can see, each player colors just a subset of the vertices from the diffusion case here. This is no coincidence. So this is always true. Everything that's colored in the Voronoi game will be also colored in the diffusion game, because if you have the unique shortest distance to a vertex, then the diffusion process will also color it for you. But it's not the other way around. So for example, this vertex up here, it has distance 2 to both players. So in the Voronoi game, it's a standoff. They both have the same distance. You need to be uniquely the closest one in order to color it. But in the diffusion game, the blue player can still color this vertex because she has a different shortest path, avoiding this standoff vertex. So she can block off her opponent here and then still color this vertex. So these are the two games we study here. So these are the static versions. As a short introduction. So diffusion games were introduced by Alon, Feldman, Procaccia, and Tenenholz in 2010. And over the last decade, they have been studied quite well. So most of the work considered the question of existence of Nash equilibria on various different graph classes, for example, path, trees, grids, cycles, and so on, also for different numbers of players. And yeah, this is quite well understood, I would say. And also for Voronoi games, the situation is similar. These have been introduced by De and Tang in 2007, and you also basically find kind of the same focus of research. Also, like existence of Nash equilibria is the question most looked at. I don't want to go into any details here, just so that you know these things exist. And now what do we do? As a matter of fact, as we all know, real world, especially social networks, they change over time. So of course it makes sense to study these influence maximization games on temporal graphs. So temporal graph games are actually rarely studied so far in the literature. So we are only aware of this, what we've just seen, the cops and robber game on edge periodic graphs, which Matthias has shown us by Erlebach and Spuler. And so what do? We kind of initiate, in some sense, the game theory on temporal graphs. So we generalize diffusion and Voronoi games to the temporal setting, and we want to analyze Nash equilibria existence on special subclasses, temporal path and cycles in this case. And our main observation is that this behavior is actually quite complex and different from the static case. So this is what I want to show you in this talk. So how do we define the temporal versions of these games? So we consider temporal graphs. We have a fixed set of vertices and some varying edges over time. So for each time step, we have one set of edges which are present in this time step. Now the temporal diffusion game is basically defined analogous to the static case, just that we use the edges in the set ET in step T. So this propagation process is, in its nature, it's temporal, right? It was kind of a propagation over time. So it's totally makes sense to actually play this game on temporal graphs. And so as a side remark, so this propagation continues on the last layer. So this is just a definition which we arbitrarily made. Because this is kind of natural. So if the coloring hasn't finished yet, so we don't have enough time layers, then we still say, okay, please continue on this last layer until the coloring is finished. This is just to be kind of equivalent to the static case, or most similar to the static game. So for the temporal Voronoi game, we also kind of say the same thing. So a player colors all vertices which she reaches earlier, and hereby we mean the arrival time of a strict temporal walk. So this is also kind of the closest version to the static game in some sense. So here we also have this condition that the last layer may be repeated arbitrarily often, so that we can still reach something and are not restricted by just this limited time horizon. And if we define it like this, then you can actually, it's kind of easy to see that if your temporal graph contains always the same edges, so it's kind of a static graph in some sense, then these definitions are exactly equivalent to the static games. Okay, let's have an example of these two temporal games now. So temporal diffusion. So here's a short temporal path graph. So the underlying graph is a path. And I draw it like this, that time goes to the bottom, from top to bottom. So this is the first time step, second time step, and so on. And we have, let's consider the following strategy. So the two players initially choose these two vertices here. Then in the first time step, of course, the blue player colors the vertex to its left. Then nothing else changes in the next step. And then in the third step, orange starts to color the vertices. And this is then the final outcome, of course. And now let's consider the Voronoi version of this same situation. They start here. Then blue kind of clearly reaches the first vertex here first, so it's colored blue. Now in the second time step, again, nothing seems to happen, but keep in mind that the blue player now reaches the third vertex, so it's now on the same position as orange. And this means that the next vertex is reached by both players at the same time and becomes a standoff. So, and this is actually true for all of the remaining vertices. So orange here only colors the one vertex. Yeah, so we see that, okay, this is quite a different outcome in the two games, and this is in stark contrast to the static case. So for the static diffusion and Voronoi games on path and also cycles, it's kind of easy to see that they are actually equivalent. So the games are doing exactly the same things, and they are always guaranteed to have a Nash equilibrium, which is kind of playing into the middle. So if both players play into the middle, then in the static case, this is always a Nash equilibrium. This is not the case here for the temporal version. So for the Voronoi game here, this is actually a Nash equilibrium, and for diffusion, this is not. So the blue player could improve by moving to the right of orange and then color the 3 vertices here. And yeah, then you can show that, okay, then orange wants to go on the first vertex and then blue wants to go next to him, and this goes on and on. So in the diffusion game here, you don't have a Nash equilibrium. Here, this thing here is a Nash equilibrium. No player can color more vertices by moving anywhere else. Okay, so we see actually, yeah, just from this example, there's quite a difference between temporal and static games. And here is the overview of our results. So we basically considered 6 graph classes. So we considered temporal, path, and cycles. So underlying graph is a path or cycle. And then 3 different versions of each of these. So the growing version basically means edges cannot disappear. So they only can appear over time. Then we have a superclass of this, which is called superset, which just says that the last layer contains all edges that were present at any time. So this can be written like this condition. And shrinking, which is kind of the opposite of growing, means that edges are only allowed to disappear. And we studied these special cases and found out the following. So this blue check means there always is a Nash equilibrium on these graphs for this game. And the black cross means we have a counterexample that this does not exist. So you can see that shrinking basically never helps. Growing seems to help pretty well, at least. So for cycles and Voronoi, we don't know yet. And superset helps for the temporal path. So this is actually quite easy because the superset diffusion game on a path basically is the same as the static case. So here it's the trivial equilibrium both going into the middle. So here's also the running time for finding this Nash equilibrium. So n is the number of vertices and tau is the lifetime of the graph. So we can also kind of efficiently find the equilibrium in these cases. So maybe I can quickly show you that this shrinking is quite bad. So here's the counter example. Here's a very small shrinking temporal path. It has only 2 layers and there's 1 missing edge, and already this is enough to have no Nash equilibrium. So the high-level idea is that this third vertex, this is kind of the interesting vertex, because a player wants to play here in order to color the 2 vertices to the left. So, but if somebody plays here, then the best option for the other player is right next to it. But then this guy is unhappy and wants to move somewhere else. So he moves here because, yeah, now he gets 4 vertices. And then again, orange could swap right to blue, and then blue wants to go back to this vertex. And we are kind of in the same situation again. So this is not a formal proof, but giving you kind of the intuition that this 1 missing edge is already enough to ensure that there's no Nash equilibrium here. Yeah, you can also generalize this example to a cycle. And you can also show that temporal diffusion and Voronoi games, they are actually equivalent on shrinking temporal path and cycles. The intuition here is that if they are shrinking, then in the Voronoi game, nobody needs to wait. So along the earliest arrival strict temporal walk, nobody has to wait because edges are only disappearing. If you reach something, then you don't wait. And this makes them kind of equivalent. And then you can prove that on shrinking temporal path and cycles, neither diffusion nor Voronoi games have a guaranteed Nash equilibrium. So keep in mind, this is already for 2 layers and 1 missing edge. Okay, so on the positive side, I want to quickly show you this result. So on a growing temporal path, you are always guaranteed to have a Nash equilibrium in the Voronoi game. So for the temporal cycles for diffusion, this proof is quite lengthy and yeah, way too much to show in this talk. So here I will quickly sketch the idea. Yeah, so this is the theorem, just stating that we always have a Nash equilibrium on this path. So we number the vertices from 1 to n. Here's an example of such a growing temporal path. So the idea of the proof is that we analyze the best responses of the players, and we do this using so-called boundaries. So what is a boundary? So we say that a vertex u, which is left of some vertex v, is called, so this is called a left boundary of v if v reaches u before the edge to the left of u appears in our graph. And this is analogous for right boundaries. So let's consider this example here. Let's consider the vertex number 3 again here. So just by definition, the vertex 1, 10, and 3, they are all left boundaries or boundaries, right boundary and left boundary. And the vertex itself is also always a boundary. And now we check what the vertex can reach. So in the first step, he reaches this vertex, but the edge to the right is already there. So this is not a boundary. Again, also here, this is not a boundary. Now we reach vertex number 2 here, and there is no edge to the left. So we will wait here in some sense. So 2 is a boundary. And then we see that also 8 here is a boundary for the vertex 3 and nothing else. So the boundaries of the vertex 3 are 1, 2, 3, 8, and 10. And the idea of using these boundaries is that, so all the vertices in between 3 and 8, the vertex 3 will catch up with them until vertex 8. So he reaches vertex 8 and then all other vertices in between, they also had to wait here. So to the right, all of these vertices will reach at the same time. So everything to the right will be reached in the same time by all these vertices in this interval here. This means that for Voronoi game, you cannot color something to the right here. And this is the overall idea why we use this boundary definition. So now the best response, we have some short observations. So these boundaries, they partition our vertices into intervals. So these are just the intervals between the consecutive boundaries. It's the same example as from the last slide. And we can see that a player can only color vertices within a boundary interval of the other player. So if orange plays here, then this lies in between this boundary interval of the blue player. And we can see that the coloring can then only be inside this boundary interval. This is kind of by definition, orange cannot color anything to the right of this interval because it's a boundary here. So blue can also reach these vertices at the same time, and also clearly not to the left because blue is there earlier, or at least as early as orange again. And now what is the best response then? Of course, the best response means, okay, let's choose a largest boundary interval of the other player. So orange is already in the right boundary interval, but then choose the vertex that's closest to the other player. So orange would need to choose this vertex here next to blue, because then we are guaranteed to color all the vertices in this interval, because so we never need to wait inside this interval. So we will always be earlier than blue. So we color all of these vertices in the interval, and then this is the best thing we can do. Okay, and this is kind of all we need. Now we can show that we understand that these are best responses of the players, and we can show that every best response sequence contains a Nash equilibrium after at most n steps. So the idea for this argument is kind of, so the best response cannot always go to one side. So it cannot always go to the right, to the right, to the right, to the right. So because the graph is finite, at some point we have to go to the other side. And we can then show by case distinction that if the best response goes in the other direction, then you found a Nash equilibrium. Okay, yeah, so this is the overall idea of this proof. So these boundaries, they help in understanding growing temporal path. So here, once again, the overview of our results. As I said, for growing temporal cycles, for diffusions, we can show something which is much more complicated. For temporal cycles, for Voronoi games, it might be possible that same arguments can work, like for the path here, using these boundaries. Maybe this also goes through for cycles. So we didn't think it fully through, let's say, but it might also work here. But yeah, we are not sure yet. Okay, so basically that's all I wanted to show you for now. So let's conclude. So in general, temporal diffusion and Voronoi games, they are quite interesting and rich of complex behavior, even on kind of the simplest graphs possible. In general, you can probably say that Voronoi games seem to be the more complicated game, and it admits less Nash equilibria. So this is our impression. And also in general, forbidding edges to disappear, this helps in guaranteeing Nash equilibria. So what we saw is that, yeah, as soon as one edge is allowed to disappear over time, you cannot guarantee Nash equilibria anymore. Okay, so what else could you do now? So of course, play on other temporal graphs. So consider other graph classes, maybe trees or grids or something, try to see which results carry over. What else could you do? You could vary the model itself. So you could, of course, consider more players, more than 2. You could consider the limited time horizon version. So you don't repeat the last layer. So this makes a difference. You can also define a different payoff, like standoff vertices can be shared by both players or something like this. Or maybe you have weights on the vertices, and yeah, you can do whatever you like here. Yeah, and also for temporal Voronoi games, you can study different distance notions, right? You can we studied strict temporal walks. You could do the non-strict thing. We don't understand this at all so far. And you can also define not earliest arrival, but fastest arrival or shortest. Maybe this also makes sense in some context. Yeah, so there are many things to play around here in these games, and maybe in most general, playing games or other games on temporal graphs is an open field which should be explored in future. So take your favorite game on graphs and transfer it to temporal graphs. Okay, so yeah, that's all I wanted to say. So thank you for your attention.